let's take a look at the three kernel languages of the three paradigms we saw in the course. So the first kernel language we saw is the kernel language of the functional paradigm, and here it is. So let me recall what the goal is of a kernel language. So a kernel language is technically a process calculus. It allows mathematically modeling the execution of the program. But instead of a traditional process calculus, which is focused on proving theorems about programming, here we choose the calculus so that it can express programming techniques that are important to programmers. So the kernel language is really focused on the programmer and the person who's using and creating programs and techniques. So in this kernel language, for example, then we have the if statement, we have the case statement with pattern matching, we have procedures, procedure call, procedure definition, we have the records, we have the numbers, so the basic data structures, and with this we can express all of the programming techniques in functional programming. So that's our first paradigm. Now let's go to the second paradigm. So the kernel language here, the blue rectangle here, is the same kernel language as the functional paradigm, and we've added some pieces. We've added cells and we've added exceptions. So the cells come with three operations: new cell, assignment, and access, and the exceptions come with two operations: the try and the raise. Other than that, it's exactly identical to the kernel language of the functional paradigm. So there's a small extension to the kernel language and also a small extension to the abstract machine to execute the new instructions and implement the new concepts. So with this, using the state here, using exceptions, we can build data abstractions, we can build all the techniques of object-oriented programming, polymorphism, inheritance, and so on, and they work quite well because we have all the concepts that we need to do them. So now let's take a look at the third kernel language we saw. This is the one for deterministic data flow. So again, it starts with the blue rectangle, which is the kernel language of the functional paradigm, and then we add here one concept, which is threads. So the basic notion of a concurrent activity, a sequence of instructions. Notice that the functional paradigm already had single assignment variables. If you start with a functional paradigm that does not have those, you have to add those too. So then we also extend the abstract machine to support threads, multiple semantic stacks, and a scheduler, so that the two pieces extra that we need. And with this, we can express all the techniques of deterministic data flow, such as the concurrency transparency, streams, agents, and so on. So these are the three kernel languages. But can we go further than that? Well, one obvious thing to do is to put everything together. Put cells, exceptions, and threads into one big kernel language where everything is there. And in fact, this is possible. This gives the shared state paradigm. Lets you do shared state concurrency. In fact, this one is quite difficult to program correctly. You have to build certain kinds of concurrency abstractions if you really want to use this, such as transactions and monitors. Otherwise, it's extremely difficult. And even with the abstractions, it's difficult to program. But another way to extend our kernel languages is, instead of adding cells, we add a communication channel. This is theoretically equivalent to adding cells because you can implement explicit state using an agent with a communication channel. So this gives message passing. And if the communication channel is a named stream, if we just attach names to streams, like I briefly mentioned in the last lesson, this gives the multi-agent data flow. In fact, message passing in general and multi-agent in particular are very good defaults, and they're in fact much easier to make concurrent programs in than the shared state paradigm. So those are two possibilities. There are even more possibilities. In fact, there are hundreds of programming languages that are actually used, thousands that have been invented, and dozens of paradigms, so many less paradigms than languages.